Now remember that we have the equation for conservation of mass that we have derived earlier. So in this equation, it has two terms. The first term is the unsteady, and this part is the part that we calculate or evaluate over the surface. So if I go and assume that the flow is steady state, so for an steady flow in which the properties will remain same over the period of time, no change in the flow field will occur over the period of time, then the unsteady part, the term time derivative term we call it, will be 0. So as a result the equation will reduce to my equation will reduce to this equation, only one term which we go and evaluate over the surface of the control volume, and this is the equation for conservation of mass for a steady flow field. Now next we will go and apply this equation to solve a engineering problem. So here consider a problem in which I have a converging duct through which the fluid is entering with a velocity v1. It has a cross-sectional area a1 at this point, and here the cross-sectional area is a2. So I need to calculate the velocity at the exit, means I need to find the value of v2. So the steps that we will follow I will now introduce. So I will now introduce the steps that we will follow to determine the velocity v2 at the exit. So as a first step, draw the control volume. The control volume is showing here with the red dashed lines. These lines are indicating the control surfaces of interest where the data is given or the information which is required to be determined. And remember that each control surface is indicated with a normal vector. So n1 is the normal vector of that surface on the left hand side, this one, and n2 is the right hand side. We also can draw the normal vector at these two surfaces, but for this problem we don't need them. Why? Because there is no fluid is coming out of these surfaces, so these are kind of solid lines, so actually we don't need, so that's why I did not draw them earlier. Now I will go and represent the velocities and unit vectors in terms of vector indices. So the flow is a steady state and aligned with the x-axis, so I can write down the equation of conservation of mass. So in this equation you can see that there is a dot product between two vectors, the velocity vector and the unit vector. So next I will go and write down the velocity vector and unit vector for each control surface for the problem. So in this way I have put down the vectors in the vector indices. You can see that the n1 vector is pointing towards the left side, so it is opposite to the positive x-axis, and that's why it has a negative sign in it. And n1 and n2 vector is positive, so no need to worry about it. Similarly, the velocity are represented in terms of the velocity vectors. So here v1 is entering, so I have write down this in terms of vector notation. Both velocities are represented in vector notations. So next I will go and apply this equation at each interface of the control volume. So next I will go and apply the conservation of mass equation at control surface 1 here. So to do that I will go and put the value here inside this integral rho 1. Now v1 is my magnitude and with the vector, and n cap is my n1, which is minus I, and the area is dA1. So this is my first term, and for the second, same thing, I shall go and apply that here. Integral rho 2 v2 I cap dot product normal n2 d area e2 0. So that is my equation that I have applied. Now I will go and simplify this equation. Density is constant, so I can take the density out, and the product of these two I dot I will be minus 1 because there is a minus sign. Now I have further simplified the area integral of area at the surface can be written like that, the whole. Thus, utilizing this definition, I have put the value of the area at control surface 1 and 2, similarly A2. Now from this equation, if I go and simplify this equation further, I can easily write down the value of V2, which is rho 1 V1 A1 divided by rho 2 and A2. So that is the equation that I have obtained to calculate the velocity at the exit of the converging duct. Now for an incompressible flow, the density is constant. So rho 1 will be equal to rho 2. So the above equation can be reduced in this form, which is here. Now in this regard, I would like to mention another important parameter. We call it volumetric flow rate. So volumetric flow rate is nothing but the area of the cross section multiplied by the velocity of the fluid coming out of that section. So this volumetric flow rate is indicated with the symbol Q. So in this regard, Q is equal to area multiplied by the velocity. So the above equation can also be written in terms of the volumetric flow rate, which is Q1 divided by the area 2. So in this equation, make sure that Q1 is the amount of the volumetric flow rate which is going into the converging duct through control surface 1. Now also note that if I indicate volume flow rate at the exit with this symbol Q2, which is multiplied by area, cross-sectional area, and the velocity V2 at the exit, then this conservation of mass will provide that the volume flow rate, which is the product of velocity and the area, will remain the same. So whatever be the volume flow rate is going in is coming out of the duct. So that is one of the major achievement that we have obtained utilizing the conservation of mass. But make sure that there are two important assumptions. One, the flow is steady and incompressible, and also the velocities are constant. Velocities are constant at this section, they are not varying. Now next, I would like to consider a non-uniform velocity or variable velocity at the inlet or exit. So it means that the velocity will be having some kind of profile. Then how can we go and apply this equation? So next we will talk about the non-uniform velocity, and then apply the conservation of mass.